Okay, so the last talk of this session is Attila on hardware-supported ORAM.
Okay, thank you very much. Hello everybody, thanks for attending our talk. So this will be about how we can achieve efficient oblivious search and update operations on encrypted dataset if we get help from trusted hardware. So this work has been done by my PhD students at University of South Florida and with our collaborator at Oregon State University. So basically, we have already seen quite a bit searchable encryption talk. Basically, searchable encryption allows us to perform search and update operations on encrypted data. And in a very, very high-level description, so what happens is that we have files, we extract our searchable tokens, we compute one-way functions on them, and then we bundle which keyword is included which encrypted file that makes an encrypted file set to remote server. And in the future, if we wanted to perform a search operation, what we will gonna do is we will compute this one-way token, we send it to the server performs a lookup, and whatever matching that, it will send back to the client. So a picture could tell us that actually, in order to achieve this goal, we have to leak significant amount of information, some of them as being search pattern due to deterministic matching, and also while we retrieve and put files to the server, of course, we are leaking our access pattern. And there are also other type of leakages that has been investigated. And also, as we have seen, these attacks can be also pretty devastating in real life, so it is desirable to minimize this kind of leakage if there is any way possible. So one way to that come our mind is obviously if we would use ORAM. For example, we are throwing an ORAM or encrypted index, get file indexes, and then for each file, whatever we are doing, update or retrieval, we can use ORAM, and if we do that, vast majority of these leakages will disappear. On the other hand, as it has been discussed before, if we are using a storage-only server with passive ORAM, such as circuit ORAM or path ORAM, which are considered pretty efficient for these reasons, there are performance bound that has been proven, which has been mentioned before. And actually, even of one of these best schemes, it has been shown that the main culprit is high bandwidth and round-trip overhead. If we are directly throwing ORAM on searchable encryption, actually, it has been shown this is very expensive. And also in our study, we have conducted experiments with some optimized implementations. A single query on an entire Wikipedia dataset may cause 100,000 round trips. So depending on the keywords, that number of keywords that you are fetching, if you are lucky, you could get like that. But if you are not lucky, you could get 7 GB, and it may take up to 7 seconds to approximately 2 hours, depending on how many files you are returning. So it appears that this is really good if we could do this, but for practical purposes, maybe we should look for other alternatives. And one of these other alternatives is, if high bandwidth is the culprit, can we bring client closer to the server? Indeed, if we are using a secure hardware for these purposes, we can move client logic in the server inside of a secure hardware, and we will perform our ORAM there. Now, instead of 20 milliseconds round trip, our delay will be just a few nanoseconds because we are performing ORAM over a secure hardware to RAM. So we have to communicate over bus. So this idea has been definitely investigated long before with custom FPGAs, and recently, since these kind of trusted execution environments become widely available, we said that, okay, so let's try to build an oblivious search and update platform with them and see if it helps. And there was another work, Zero Trace actually, that has actually constructed such an ORAM primitive before. So the main contributions of these papers, that will be a brief takeaway for you as well. So we have constructed a new oblivious search and update platform that harnesses Intel SGX. And what will gonna happen is that we are not creating a new algorithm here. What we are doing is that we are trying to identify most suitable primitives that we could find, implement them as efficient as we can do, integrate them together, and see how far we can go. So we choose a recursive circuit ORAM and oblivious data structures. And we are trying to respect the limitations of hardware, such as limited memory. While we implement ORAM in this hardware, we don't want to leak additional information because of the conditional branches. We were cognizant about these things. And also, we have implemented and evaluated on these things for large databases. With the large database, we means more than the 27 GB. In searchable encryption, total number of keyword and file pairs is a metric, and this could be considered relatively large for searchable encryption domain. And our code will be publicly available soon, so my student is cleaning up our messy code right now, but hopefully it will be ready soon. And also, as a very brief demonstration how much we can gain, we have already discussed what happens if you are using conventional SE over the network with ORM. If you wanted to fetch everything inside of SGX, that is another alternative we can consider, your delay will be around 131 to 157 seconds. And if you are using our platform, at the worst case, you will save a good 40 seconds. And if you are happen to fetch 2 or 3 files instead of a lot, you can be as efficient as 250 times in average for search. And if you are doing update, this could go up to 1,000 times, again, depending on the operations that we are performing. So as a takeaway, so if you accept and trust this hardware, then this might be an alternative way to conduct oblivious search and update operations. So now about the primitives that we are using, I think this has been discussed several times. We are using an enclave that offers hardware-isolated, encrypted, integrity protected memory. We will perform our ORM operation to untrusted memory region by using this. So again, for ORM, it has been also discussed in Zero Trace. It appears that circuit ORM is a suitable ORM primitive to use on SGX. It is because in circuit ORM, once we perform a read operation on the ORM tree, we are storing only one block in the stash, which is a good thing for keeping stash under control. And once we do eviction, this eviction is deterministic as opposed to probabilistic eviction of path ORM. So stash, we cannot avoid storing it at the client side. We have a position map in any tree-based ORM, which is size is linear initially. But if we perform a recursion on this position map, we can reduce its size, and that is what we will be using in our constructions. So there is another alternative to do so. And if our data is already structured, basically we can form it in a linked list. Then actually we can use ODS. And in ODS, instead of storing whole position map, you are storing the roots of the nodes in the position map. And this will allow you naturally to reduce the size of your position map. And if there is an opportunity, we will also use ODS in our construction. So let's see our setup. It is a very traditional searchable encryption setup. So extract keywords, build and index. We are constructing a linked list ORM blocks as it is very common in inverted index constructions. And upon that, what we will gonna doing is we will construct a position map for keywords and files, which will include a hash table which will associate which keywords appear in which file, which is very typical in searchable encryption. It is very difficult to get rid of. And we will also have a position map, and this position map we will be storing head of each of file and keywords with a recursive ORM structure. For our encrypted linked list, since it has a structure, we can utilize an ODS to bundle them. And also for file themselves within Insight, we can represent them in a linked list form, and therefore we can use ODS again. So once we obtain all these bundles that we call, we are sending them into untrusted memory. Now we are moving into first update operation we will present. Let's say we wanted to add or remove this file, extract keywords, send it to the enclave. What we will be doing is that first we wanted to get the first ID block for each keyword in this file, and we are scanning entire hash table. You may ask why you don't throw ORM on it. We are not aware very efficient ways to throw ORMs on hash tables because there are collisions. Size of this hash table is 188 megabyte, and it took 209 milliseconds to fetch it. Therefore, we justify that this fetching directly is a practical approach at this point. After this has been obtained, what we will gonna do is we will use an ODS controller to update our encrypted index. In here we are using a lazy deletion and addition strategy, meaning that we are not traversing entire linked list. If we wanted to add or delete, we are adding a pointer information into linked list, which we will clean up later. After this has been done, right now encrypted data structure is updated. For the file, we are getting relevant file, the position of first block, by using a circuit ORM controller. And after this is being done, now we can perform our ORM operation on ODS data structure for the file components, and update operation is done. So, and finally for the search operation, which is very similar, we are sending keyword to the enclave. Again, we are scanning entire hash table, obtain corresponding block and path ID. Then we are going to the ODS controller, and we are fetching necessary file IDs corresponding to this. One thing we are doing is that since we are doing lazy addition and deletion, size of our linked list will grow by time. During the search operation, we will traverse entire linked list. This gives us an opportunity to eliminate redundant information that we have added in lazy deletion. So we will sanitize them. We will obtain file indexes. And then again, now for each file, head of the file, we throw an ORM to recursive circuit ORM. And then for each of them, then we are throwing an ORM to ODS controllers, get relevant files, and send them back to client. So as you can see, what we are doing here is an optimized implementation, identify correct bundling and primitives, and use them together. That's what it is. So while we do so, we linearly scan hash table, as I discussed. I do not think we can avoid linearly scanning stash 2 that we did. And here, while we do these things, it has been shown in previous studies that actually conditional branches may also leak information, and there are special instruction sets that must be used to avoid these particular leakages. This has been taken into account in our implementation, as suggested in previous work. So for experiments, these are our experimental setup. I will not enumerate them one by one. Basically, what we are mainly comparing is we are mainly comparing path ORM plus searchable encryption plus ODS. We choose path ORM over circuit because it is a little bit more efficient on network setting. And another comparison will be done processing entire index and database inside of SGX. So as we can see here, what we are doing is that first we are comparing, depending on number of files returned to the server, how our delay increases. So for vast majority of the wiki data set, for 99.5% of the keywords, you return less than this much file. In these kind of settings, we can observe that actually this platform performs better than fetching everything inside of SGX, and under any condition, it will perform better than doing ORM over the network. And the reason that obviously this is faster than doing over the network is that we do not have a network bandwidth blowup because we are using a secure hardware. That is why it is better than doing over the network. And why it is better than fetching everything inside of the SGX is then again, for vast majority of the keywords, if you are downloading less than this number of files, our approach will be faster than fetching everything inside of the SGX. But for small fraction of keywords, you are approaching to download everything from database. In this case, using ORM is not good. It is better to download everything, and then entire SGX will be better than our construction. For update, similar results, for approximately 40 times better than doing over the network. This time we are a little bit more better than fetching everything inside of the SGX. Why our efficiencies increase a little bit? It is because we were using, you may remember, this lazy addition and deletion strategy. What happens is for per update we are just adding one block to the linked list. This is better than downloading everything inside of the SGX, obviously. So that is why and both actually network ORM and POSUP get benefit of that strategy. So yeah, basically for our storage, for 27 gigabyte wiki set, our total storage is 170 gigabytes. So obviously there is some storage blow up, but we think it is potentially tolerable for some real life applications. Yeah, in conclusion, so what we have done is we have developed an SGX supported OWS search and update platform. The contribution here is to collect best primitives that we know of, implement them as efficiently as possible, and conduct experiments. And we believe if you can tolerate the presence of a secure hardware, this is potentially a way to eliminate leakages in searchable encryption. And our limitation is right now we have only single keyword. We can extend to multi-keyword, but it will be expensive. So we are right now, as I said, we are downloading a keyword hash table directly. We don't know how to throw an ORM on it efficiently. If we can do that, we can make that number go down. And we will investigate how we can support more diverse queries. Okay. Thank you very much for your time.
Any questions?
Thank you for your talk. Considering the deployment model, in your case, the SGX is locally deployed. If you consider that you should have the SGX on like remotely deployed, in your case, how would the performance affect it in this case?
Remotely deploying SGX meaning?
I mean, there's a remote connection. I mean, for example, for another party. I mean, the SGX deployed by another party.
So in our setting, the client has. So if you go back to here, so actually let me go back to. Yeah. So in our setting, we are in single client setting. We are unable to do multi-user searchable encryption on ORM, if that's the question. And this client will control the ORM controller with her own private key. So SGX has to be local into server in order to get the benefit of these performance benefits. So this is currently our setting. I do not know how a remote controlled SGX would work in this setting. Maybe we can discuss offline on that.
Yeah, sure. Thank you.
Mm-hmm.
Thank you for that.
You just need to speak up.
Okay, thank you for the talk. I was just wondering if you have looked into some of the optimizations on circuit ORM which sort of delay the eviction, because the eventual objective for that is to keep the stash size low, and there are some optimizations there. So have you looked into and how they affect your overall performance?
So I think my student has, he said, spent significant amount of time to use an optimized version of circuit ORM.
Okay.
So potentially he did, but I don't know.
Okay, cool. Thanks.
Yeah, so this is not really a comment about your work, but it's more about some of the papers that you cite in terms of the attacks. It turns out that actually, like the attacks, like one of the papers, the attacks don't work, and the other ones work under very strong assumptions that are questionable in terms of whether they're realistic or not. And it turns out that under that same model, you could also attack ORM under the same model as those attacks.
Okay,
I mean, that doesn't mean that, ideally this is sort of really nice because you still remove the leakage, but there's sort of a general misconception about how the attacks work and what they do.
So you mentioned before that you're looking at this single client case, and so the client, I guess, has to authenticate using whatever means to the SGX enclave. So what is the limitation that prevents you from doing the multi-client situation, given that all of the secrets that are needed for the ORAM are contained within SGX?
So actually one thing we could do is that we could create an access control model for that. So we could create a master key for entire bundle. And actually there is not a significant, in my opinion, it's a more engineering task, I would say. We are working on a paper that does that multi-user oblivious searchable encryption that we are working on right now. So it can be done, but it requires an ORM supported access control mechanism.
Okay, so it's not viable then just to leave the client unauthenticated and let anyone access this thing.
Could you say again?
So it's not viable then just to let the client be unauthenticated and make this publicly accessible, but
No, I don't. Not in this model, at least.
Thanks. You have one quick question? Yeah. Quick final question.
So you mentioned zero trace in the talk, and I was just wondering, what's the general difference between your work and zero trace, and is there a specific reason you did not compare, in the graphs you did not compare to zero trace?
The reason is, first of all, while we write in this paper, we checked if code of zero trace was out. We couldn't find, and that is why we implemented ourselves. To us, zero trace is an ORM primitive. We could directly use it to achieve this objective. So that is why we didn't compare. So it is not our counterpart. It is a primitive that we could have used if it would be available. It is available. It's available now? Okay. Once we do this, we checked and we couldn't see it.
Okay. Let's thank Attila again. And that concludes this session. So.